Hello, welcome to is it our third video? I can't keep track anymore. The days just seem to run into the other, except that tomorrow's Monday and I wanted to have a lesson for you for tomorrow. I figured it's been since Wednesday since you've done any physics. You're probably missing it somewhat, so here we go. What we're working on today is momentum and impulse. And momentum is used often in the English language, talking about different things. Sports uses it often. One team has momentum over another team and so on. In physics, we define it really specifically. It's defined as the product of mass and velocity, and it's a vector. Now, I think I was a bit remiss in the energy unit. I didn't talk enough about energy being a scalar, and I just don't know if you remember what the difference between a scalar and a vector is. We'll just do a quick reminder right here. So, if we think about displacement and distance, we know that distance is a scalar and displacement is a vector. And many times, scalars are far easier to use than vectors. If I said to you, for example, you went on a run, you went 5 kilometers north, then 6 kilometers east. If I said to you, what's the distance traveled? You'd say, well, that's really easy. The distance traveled is just the addition of those two things. So 5 plus 6, 11 kilometers. If I said to you, what's the displacement? That's not quite as easy to figure out. So the displacement, in case you can't remember, that's the distance you are from the start. So we started here, start. We finished here, finish. So our displacement is that right there. Now at first we're going to have to use Pythagoras to get that hypotenuse length in, provided I drew that properly at 90 degrees. And then we'd have to find the angle there as well to give a proper full answer. Because as you might remember, vectors have to have a magnitude, which is the number, and a direction as well. So when we're back to this, we're talking about momentum as a vector. Energy is not a vector, and let me explain a couple of things. I've got a little demonstration here I want to show you. So let's pretend that these two, I think they're Thomas the Train, and oh wait, this one might have it written on the side. Oh, it doesn't. Oh, Toby. Okay, so Thomas and Toby are coming towards each other. Now let's talk about energy first. If I told you the mass of Thomas and the speed of Thomas and the mass of Toby and the speed of Toby, and I said, how much energy do we have? You could find it out really easily. You'd say the kinetic energy of Thomas plus the kinetic energy of Toby, add it together, and that's how much energy our system would have. Now for momentum, that's much different. I'm going to make up some simple numbers for you. Let's pretend Thomas had 10 kilogram meters of momentum this direction. Toby had 10 kilogram meters of momentum in this direction. That means that the sum of their momentums is 0 because they're vectors. One would have a positive momentum one way, one would have a negative momentum the other way, and when they crash together, they would have no momentum. Just as they had no momentum here, this one would cancel out this one. So, let's keep on with our notes. The units of momentum are either kilogram meters a second, and you can see the derivation right from the formula. There's meters. No, that's not meters. There's mass, so that's kilograms. And that's velocity, meters a second, right there. So that's where our units come in. P is what they use for the symbol for momentum. It's a lowercase p, because of course we don't want to mix it up with power, which is an uppercase P. I think I looked up somewhere, the reason they use P is because in a different language it was for impetus, hence the P in impetus. So P is momentum, M is mass, and V is velocity. So the first thing we're going to look at is conservation of momentum. Last unit with energy, we did conservation of energy. And so it says here, in any collision or explosion. Now, I had a student once say to me, can we just consider an explosion a collision backwards? And after a bunch of thought, you can. It works just fine. Which is a really weird thing to think about. Anyway, where you consider all of the parts or the system, momentum is conserved. And whether something is conserved or not means the initial, in this case momentum, equals the final momentum. So in these questions that we're going to look at, I always like to draw before and after pictures. And that makes my life just a little bit easier. So, a 75 kilogram rugby player is stationary when she is run into by a 94 kilogram player traveling at 74 meters a second. Nope, 7 meters a second. They become entangled after the collision. How fast do they move immediately after contact? So I do apologize for my pictures. You know that they are never very good. I'm going to do squares because I can draw squares sort of effectively. So we've got this 94 kilogram player going velocity 7 meters per second this way into a quite possibly unhappy stationary player. So this is my before picture. So before the collision, and I just do a little line there to say this is the before picture. After the collision, they're together. So I've got this one is 94 kilograms, this one is 75 kilograms, and I do not know the velocity. So there's my before picture, my after picture, and from here we're going to do the formula a couple of times, and I think it'll be just fine. Again, like the last unit, the math isn't particularly difficult in these cases. That's going to be probably easier than it was last unit. So what I want to write down is my momentum. So P initial is the momentum of this player plus the momentum of this player. So remember from our formula here, momentum is mass times velocity. So my mass is 94 times 7. Plus, normally I wouldn't write this one in, but I'll do it for now just because this won't always be the case where the second person is 0. So there's my other mass times velocity. We'll do some number working in a minute. P final is the momentum after the collision. And I've got my two masses added together, so that's going to be 94 plus 75 times the velocity, which I don't know, so I'll call it V. Well, let's do some calculations here. So I'll just do 94 times 7. I get 658. So my initial momentum is 658. We'll put some units in, kilogram meters per second. My final momentum, 94 plus 75 is 169, so it's 169 V. And at this stage, I always say to the students, what does it mean to say that momentum is conserved? And what it means is that P initial equals P final. And so here, I've got my P initial is 658. I'm going to just jump below this black line. Equals 169 V. And you're going to divide both sides by 169. And so we'll get... we will get 658 divided by 169, and we get 3.89 meters per second. Now, we're asked for how fast. If you're asking for how fast, that's a speed. Speeds are scalars, no direction is required. Just out of habit, I always write a direction in. So in this case, it'll be 3.89 meters a second in the direction of the 94 kilogram player. Okay, here's our second one. In the trailer of a great Canadian movie, the 20 kilogram curling stone is thrown at 7 meters a second. It explodes into two pieces. One piece, mass of 12 kilograms, goes forward at 58 meters a second. What is the velocity of the other piece? So here's some hints about what movie I'm talking about, because you probably don't care about the physics question. Here's the two hints. Is there two hints or three hints? Okay, I'll give you three hints. The first hint is it had what I think was the greatest Canadian comedian, acting comedian ever, starring in it. He's not alive anymore. The second hint is one of Canada's favorite bands had a cameo appearance as a curling team in it. And the third hint is the actor was very well known for playing a Mountie. And I don't remember what show it was on. Anyway, if you're not sure, you can search it up, or you can send me a note. Okay, so again, start with the picture. So the before picture, we've got a 20 kilogram curling stone thrown at 7 meters a second. So before, we've got this. So 20 kilograms, and the velocity 7 meters a second. I'm just going to put an arrow in. That's all I've got. So the before picture is pretty easy. Notice I'm asking for velocity, so we're going to need a direction. So here's the after picture. I do apologize again for how bad my artwork is going to be. So it explodes into two pieces. The 12 kilogram piece, which is obviously the bigger of the two pieces. 12 kilograms. It looks like a Pac-Man ghost, doesn't it? V 12 meters a second this away. And my other piece, an 8 kilogram piece. The 8 kilogram piece should be, of course, smaller than the 12 kilogram piece, but that's my art. I don't know. So, same steps as the last one. We're going to say what our P initial is and what our P final is, and we'll make them equal. So P initial, I don't even need a calculator here. P initial, remember P is M times V. So there's M times V. I'll write it out for you. 20 times 7. So it's 140 kilogram meters a second. I'm going to put an arrow in. Just that's going to be important in the next example. Okay, P final. It's 8 times V. That's like the worst 8. 8 times V plus 12 times 12. Again, M times V. Who wrote these questions? Who would do it at 12? 12 times 12? No, that's not 12. That's 58. Oh, man. Guess I will need a calculator for this. So this is 58. I was thinking too much about that great band. And I hint about the great band. The lead singer passed away a couple of years ago. That's probably giving it away now. I can't remember if the movie's any good or not. I just remember at least sometimes stupid bits of trivia. Okay, so 12 times 58, 696. So we get P final is 8V plus 696. And again, momentum is conserved. So we say P initial equals P final. So 140 equals 8V plus 696. Now, we're going to get the V by itself. I'm going to subtract 696 off each side. So we'll go 140 minus 696, and we get a negative number. I'm hoping that some of you are thinking about what that negative number means. And so we'll divide both sides by 8, and we get negative 69.5 meters a second. So, any guesses on what that is? And of course, it means that it's in the opposite direction. So my velocity is 69.5 meters a second, and you can say backwards. I think that's a totally acceptable way to state a direction. So it's backwards or in the opposite direction of the original stone or something like that. Backwards is fine. Just don't leave the negative in. Interpret the negative. And there we go. Okay, one more example to put up with here. So we've got a 9 kilogram ball traveling at 15 meters a second right when it collides with a 5 kilogram black one traveling at 20 meters a second left. After the collision, the black ball is traveling at 8 meters a second right. What is the velocity of the red ball? So there's a whole bunch of stuff going on here. And if you try to write out the formula without keeping things in your mind, you're going to get lost. So do a picture, a simple picture. I use red and black because on the smartboard I had red and black crayons. I don't think I have that here at all. Oh, I've got red. Oh, I do have red and black. Okay, so here we go. So a red ball is traveling, here's the red. Okay, 9 kilograms, going 15 meters a second to the right. I once had a student ask me, how do I know whether to put the red ball on the left or the red ball on the right? And I said, if we have them mixed up the other way, there's never a collision. Kind of a good question though. And the black ball, 5 kilograms traveling left, so there's 5. Again, I'm not super worried about size, but I draw these things. So that's going that way at 20 meters a second left. Okay, so this is my before picture. Okay, my after picture. What do we say? After the collision, the black ball is traveling at 8 meters a second right. So I've got this as 5 kilograms. It's going the other way. And the red ball, I don't know what it's doing. But our steps are exactly the same. So just as in this last example, where we ended up with a negative and we had to interpret it properly as it going backwards, here we're going to have to choose a direction to be positive, because I've got one going right and one going left. And just generally I just say right is positive. Mathematically, on the x-axis, going to the right is positive. I can see the black ball afterwards is going right, so I may as well make right positive. And it's the same steps as before. So P initial, we've got m times v, and this is important. This is where the mistakes are going to be made. And here it's 5 times negative 20. And again, it's negative because it's going left. It has to be an opposite sign from the 15. There's nothing that says you can't make right negative and left positive, but just I'm going to make this choice for this one. Okay, so P final is 9 times v. Again, I don't know what v is, so I'll just leave it there. And this is m times v, so 5 times 8. We'll work out how much, we'll work out what we can. So pi, 9 times 10 is 90, and 9 times 5 is 45. So I guess that's 135 plus negative 100, and that gives me 35. Okay, so P final is 9v plus 40. And again, the same steps. I'll say to my students, if I had you in front of me, I'd say, what does it mean to say that momentum is conserved? And somebody would say, it means the P initial equals the P final. And here we go, so 35 equals 9v plus 40. We'll bring the 40 over. Ooh, look at that. It looks like we're going to get a negative. And so we're going to get negative 5 equals 9v. We'll divide both sides by 9, and we'll get v equals negative 5/9, which of course is negative 0.55 repeating. And we will say v equals negative, no, I didn't want the negative in there. V equals 0.556 to 3 significant figures, meters a second. Then now we have to interpret that negative, and the negative of course means it's going left, and that's fine just to say leftwards. So there's a couple of more things left, but before I go on to those things, I wanted you to get a chance to look at this and do these questions. I think this is probably going to be easily the rest of the time for you this week to work on the questions I've assigned. We'll do another part next week. We'll talk about energies before and after the collisions. It's not a huge amount, but it just adds some complications that I didn't want to deal with right now. I was super happy with how you guys did in the tests. I thought you did great. I think your ability to adapt to these strange situations is phenomenal. It was great to see. It was great to see some really good work in those questions. I'm going to leave it at that. I hope you all have a great week. Thanks. Bye.